Good afternoon, students. Today in physics we will study about simple harmonic motion. Our objectives will be: what is simple harmonic motion, what do we mean by periodic motion and oscillatory motion. We will take up some examples of these. Then what is displacement in simple harmonic motion, velocity, acceleration and relationship between displacement, velocity and acceleration. Then we will study about simple pendulum and spring mass system, and finally we will talk about free, forced and resonant vibrations. First of all, let us see what we mean by simple harmonic motion. Nature follows periodicity. The day and night, दिन तो बाद रात, रात तो बाद फिर दिन, life and death, everything is repetitive, repeat करता है. So periodic motion is that motion which repeats itself after a fixed interval of time. There are many types of periodic motion, and the simplest of the periodic motions is called simple harmonic motion. In simple harmonic motion, displacement, velocity as well as acceleration, all these are sinusoidal, means follow sine curve. Any vibrating system where the restoring force is proportional to the negative of the displacement is said to be in simple harmonic motion. Sometimes we also refer to it as simple harmonic oscillator. कोई भी सिस्टम जो वाइब्रेट करता है, रिस्टोरिंग फोर्स मीन रीस्टोर करना, उसनों वापस लेके जाता है जो फोर्स. अगर वो रिस्टोरिंग फोर्स डिस्प्लेसमेंट दे प्रोपोर्शनल है और उसके अपोजिट डायरेक्शन च है, then that is called simple harmonic motion. So simple harmonic motion is the motion that repeats itself after regular time interval such that the force acting on it is directed towards its mean position or any other fixed point in its path, and the force is also proportional to the displacement of the particle from that fixed point. Periodic motion is that motion, as I told you beforehand, which repeats itself over and over again after a fixed interval of time. The fixed or regular interval of time after which the periodic motion is repeated again and again is what is called its time period. ਤਾਂ ਉਹ टाइम ਜਿਹਦੇ ਵਿੱਚ ਕਿ ਇਹ periodic motion repeat ਕਰਦਾ ਹੈ, ਉਸਨੂੰ ਅਸੀਂ time period ਬੋਲਦੇ ਹਾਂ. This is one example of the periodic motion. The rotation of earth about its axis with period of rotation of 1 day. ਧਰਤੀ ਆਪਣੀ ਐਕਸਿਸ ਦੇ ਆਲੇ ਦੁਆਲੇ ਆਪਣੇ ਧੁਰੇ ਦੇ ਉੱਤੇ ਇੱਕ ਦਿਨ ਦੇ ਵਿੱਚ ਘੁੰਮਦੀ ਹੈ, rotate ਕਰਦੀ ਹੈ. This is an example of periodic motion. Revolution of earth around the sun, you know, earth revolves around the sun and takes a time of 1 year. After every year it comes back to its original position. Like here you have summer in the northern hemisphere, here you have summer in southern hemisphere. So this is how, this is Earth's orbit. Earth is revolving around the sun. और इन्हां पोजीशन ਦੇ ਉੱਤੇ हर एक पोजीशन ਦੇ ਇੱਥੇ 1 ਸਾਲ ਬਾਅਦ ਆ ਜਾਏਗੀ अपनी पोजीशन ਤੇ अर्थ रिवॉल्व ਕਰਨ ਤੋਂ ਬਾਅਦ. After every year it comes back to its original position. Mean this is also a periodic motion. Moon revolves around the earth and takes a time of 27.3 days. So this is the time period of the moon. Time taken to rotate once around the earth by moon. Again this is a periodic motion. After every 27.3 days the moon will be at its original position. Phases of moon, as the moon makes its monthly journey around the earth, side of the moon reflecting the sunlight is viewed from different angles. These are the phases: new moon, waxing crescent, waxing half, waxing gibbs, full moon, waxing waning gibbs, waning half, and so on. This is another example. The animation shows different phases of the moon. As the moon revolves around the earth, you see, when it comes here, it is full moon. This is moon's phase as has been observed from the earth's surface. Then what is oscillatory motion? A motion that repeats itself over and over again about its mean position, such that it remains confined within two well-defined limits. These two well-defined limits are called extreme positions on either side of the mean position, that is a fixed point. So, oscillatory motion भी periodic ही होया, but there is a constraint here. If you read it again, the motion that repeats itself over and over again. This is what we had meant about periodicity also. Read the next line. It remains confined within two well-defined limits. Means its motion is bounded. और उत्ते कंस्ट्रेंट है, इन्हां दो एक्सट्रीम पोजीशन तो बाहर नहीं जा सकता, इन्हां दो पोजीशन के विचाले ही रिपीट करेगा. पीरियोडिक मोशन की सी? रेपीटेटिव मोशन. पर अगर ये रेपीटेटिव मोशन दे उत्ते कंस्ट्रेंट लगा दिता जाए कि इट इज टू बी विद इन वेल डिफाइंड लिमिट्स, then we call it as oscillatory motion. So, we can say that a periodic and bounded motion of a body about its mean position is what is called an oscillatory or vibrating motion. So, it follows that all oscillatory motion are periodic motions, but all periodic motions are not oscillatory. जिन्ने ऑसिलेटरी मोशन हैं वो सारे पीरियोडिक मोशन जरूर हैं, पर सारे पीरियोडिक मोशन ऑसिलेटरी नहीं होंगे. Some examples of oscillatory motion, like when a liquid in a U tube is displaced, it executes oscillatory motion. When a load attached to a spring is pulled once a little from its fixed point and left, it starts oscillating. स्प्रिंग नाल मास लग्या है, तुसी उस मास नूं थोड़ा नीचे नूं खिंचो तां स्प्रिंग ऊपर नीचे वाइब्रेट करना शुरू कर दिंदा है. दिस मोशन इज कॉल्ड ऑसिलेटरी मोशन. इफ यू हैव अ वॉल क्लॉक, देयर इज अ पेंडुलम इन इट. द मोशन ऑफ द पेंडुलम ऑफ ए वॉल क्लॉक इज अगेन एन ऑसिलेटरी मोशन. A glass ball dropped along walls of a semi-hemispherical bowl and released will also show you the oscillatory motion. This is the wall clock, this is the pendulum here, it will vibrate to and fro. So, there will be two bounded, two extreme positions, two boundaries within which it can vibrate, it cannot go away from that. This is an oscillatory motion. If you see, the ball is oscillating, but it has got a limit, it has got a boundary. एक इधरली साइड ਦੇ एक्सट्रीम पोजीशन है, एक दूसरी साइड ਦੇ एक्सट्रीम पोजीशन है. इदा ही ਤੁਹਾਡਾ वॉल क्लॉक ਦੇ ਵਿੱਚ जो पेंडुलम है वो वाइब्रेट करता है. इफ यू ट्राई टू पुट लिटिल ब्रेन इनटू इट, यू सी जो पेंडुलम वॉल क्लॉक ਦੇ ਵਿੱਚ है वो भी इसी तरह वाइब्रेट करता है. दो एक्सट्रीम पोजीशन, दीज वाइट कलर्ड रॉड्स दे शो द टू एक्सट्रीम पोजीशंस. द बॉल डज नॉट गो out of these two extreme positions. This is a ball which is being moved within two limits on a semi-hemispherical bowl. So, semi-hemispherical bowl है, ball ਨੂੰ एक सिरे तो छड्डोगे, it will start moving like this. This is again an oscillatory motion. Limit है, boundary है, periodic जरूर है, you see it is repeating itself, repetitive motion है, so it is a periodic motion, but it has got two limits, it does not go out of this side or this side. So, there is a boundary, there is an extremity, bounded motion है, periodic तो है ही है, that motion is called oscillatory motion. Now, let us study about Hooke's law. The restoring force of an ideal spring is given by F equal to minus kx. What do we mean by this? That restoring force will be proportional to the displacement. You have a ball here, जिन्ने force नाल तुसी इसनू इधर नू खिंचोगे उन्ने force नाल ये restore होएगी. Larger the displacement, larger will be the restoring force. K is called spring constant, it is a proportionality constant which we call spring constant. It is defined as restoring force per unit displacement. X is the displacement of the spring from its unstrained, from its mean position. Mean position तो कितना तुसी इसनू खिंचा है उसनू असी displacement कहने हैं. Negative sign indicates that restoring force always points in a direction opposite to the displacement of the spring. You see, if the spring is being displaced in this side, then a restoring force will be in the opposite order shown with blue colored arrows. Displacement right side नो है तो restoring force left side नो होएगा. अगर displacement left side नो है तो restoring force right side नो होएगा. So, restoring force is always pointing in a direction which is opposite to the displacement of the spring. One of the properties of elasticity is that it takes about twice as much force to stretch a spring twice as far. अगर तुसी let us say you have displaced the spring by 10 centimeters, you want to displace it by 20 centimeters, then the force required will be double as compared to the first case. So, this is what we call as linear dependency of displacement upon stretching force. Again, this is Hooke's law. You have a spring here, you put a ball here, this ball forces it downwards, let us say it gets displaced by distance x. If you want to stretch it by distance 2x, you will have to apply double the force. So, stretching force is directly proportional to the displacement. If you stretch it by twice the length, the force will also be twice, and if stretching force is twice, restoring force will also be twice the value, double हो जाएगा. Simple harmonic motion, this is the unstrained length. If you see here, this is a spring, a ball is attached to the spring, then we just drop it, leave it, it will get stretched by a certain amount, let us say d dot. This stretching is under its own weight, जो ball the weight है उस weight दे अंडर है stretch हो जाएगा. Now, if you displace it slightly downwards, इसनू पकड़ के नीचे नू तुसी छड्डोगे, it will start vibrating. These vibrations are then called simple harmonic motion. So, when there is a restoring force F equal to minus kx, simple harmonic motion occurs. Now, how do we compute for the displacement in simple harmonic motion? Simple harmonic motion can be considered as to be a circular motion. So, let us say the body gets displaced to point P, then if this is angle theta here, then OM divided by OP will give you sin theta, or OM is equal to OP sin theta. OM is the displacement in the y direction, R is the radius of the circle, amplitude also you can call it. So, it is the maximum displacement from the mean position. When you are moving in a circle, the maximum displacement can be the radius of the circle. So, displacement in the y direction is equal to amplitude times sine of the angle of the particle from its mean position. This is the mean position. So, y is equal to r sin theta. You know from your studies about rotational motion that angular velocity is equal to angular displacement per unit time. So, angular displacement is angular velocity into time. So, you can replace theta by omega t, you get y equal to r sin omega t. Then we can compute velocity in simple harmonic motion by the formula v equal to omega under root of r square minus y square. Let us say the body is moving in this direction, say with an angular velocity omega, the particle or the body is at point P making an angle theta from its mean position. The blue colored line gives you the mean position of the particle. The velocity at any point is given by the tangent drawn at that point. So, draw a tangent at point P, Pk is the direction of the velocity and also gives you the magnitude of the velocity. So, if angle is theta at the center, angle here is 2 theta, this is also theta. So, cos theta is OQ divided by OP. Why are we taking OQ? Because you see this component is required. So, Pn is the component of velocity which is along the displacement, because displacement was along OM. You do not require this component. This is a perpendicular component of velocity which does not contribute to the motion of the particle in the y direction. जिधर ਨੂੰ direction हैगी है, जिधर ਨੂੰ displacement हैगी है, ਉਹ ਉਸ ਕਰਕੇ ਹੋਏਗੀ ਅਗਰ ਉਧਰ ਨੂੰ velocity ਹੈ। ਸੋ velocity ਦਾ ਉਹ component ਲੈਣਾ ਹੈ ਜੋ ਕਿ displacement ਦੇ parallel ਹੈ। So, displacement is being taken along OM, component of velocity which is along OM direction is Pn. So, we are interested in Pn component and not in Pm component, because normal component of velocity does not contribute anything to the velocity of the particle. So, Pn divided by V gives you cos theta. This means Pn is equal to V cos theta, and we had studied that theta is equal to omega t. So, V is equal to cos omega t. If you see from this triangle OPQ, this is a right angle triangle, we can compute cos theta here. What is cos theta? Base divided by hypotenuse. Base is OQ, hypotenuse is OP. Now, what is OQ then? Use Pythagoras theorem, it is OP square minus OQ square. OQ is OP square minus PQ square, the under root. So, r square minus y square, the under root divided by r gives you Pn equal to V under root r square minus y square upon r. V you know is equal to r omega, r cancels, you get V equal to omega under root r square minus y square. Now, if y is equal to 0, means when displacement is 0, velocity will be how much? Y is 0, r square the under root gives you r, V is equal to r omega, this is the maximum value of velocity. And when y is equal to r, mean the particle has reached this point, then y is equal to r. So, r square minus r square gives you 0, velocity becomes 0. So, at this point velocity becomes 0, the particle starts travelling backwards in the downward direction towards the mean position, reaches the other extreme, comes back to its mean position. This is how the particle oscillates between these two limits. Velocity is maximum, as I told you, when y is minimum, and velocity is minimum when y is maximum. When displacement is 0, velocity is maximum. When displacement is maximum, velocity is 0. This is how you can show the position versus time graph. This is the spring that will be moving in between two positions. This is called the amplitude, maximum displacement from the mean position. So, what do we mean by amplitude is maximum displacement from the mean position. This is the mean position. So, the curve that you will get will be a sine curve. If you take displacement along the x axis, it will be like this. As I told you, we can consider simple harmonic motion as consistent with uniform circular motion. This is the rotational vector. The particle is moving around in a circle. Amplitude is a, which is also equal to the radius of the circle. Phi is the phase angle between this point and this point. Now, if there is already, as I told you, if you see the last slide, the angle was phi, particle was already positioned at point phi. Now, the particle has moved through angle omega t. So, total angle from the mean position is omega t plus phi. So, phi is called epoch. Epoch means initial phase, initial position किसी particle दी, that is being given by phi. So, x, this is displacement in the x direction, divided by a gives you cos theta, and theta here is omega t plus phi. So, displacement becomes a cos omega t plus phi. If there is no initial phase, if there is no epoch, if phi is equal to 0, then x is equal to a cos omega t. Now, if you see on your screen, this slide shows you all three, that is displacement, velocity and acceleration. Displacement, as we had done, is equal to a cos omega t plus phi. If you differentiate it, dx by dt means time rate of change of displacement will give you velocity. Cos omega t plus phi gives you sin omega t plus phi with a negative sign, and you have omega with t, you get minus omega a sin omega t plus phi. As I told you, omega a is the maximum velocity. So, we write it as v maximum, and instead of minus sign, the relationship you can write it as cos omega t plus phi by 2. If you compare these two equations, the one giving you the displacement x and the other giving you the velocity of the particle, you see the difference in phase is pi by 2. X is a cos omega t plus phi, whereas v is equal to v m cos omega t plus phi plus pi by 2. So, the phase difference between displacement and velocity is pi by 2, 90 degrees. So, if displacement starts from here, velocity starts from the 0 point. If you see and compare these two curves, when velocity is 0, displacement is maximum. When displacement is 0, velocity is maximum. Again, if you differentiate this equation that gives you velocity, this will give you acceleration. dv by dt means time rate of change of velocity gives you acceleration. Again, you differentiate it, you get minus omega square a, because differential of sin omega t plus phi is cos omega t plus phi. So, you get minus, and the term multiplied by t is multiplied outside, you get minus omega square a cos omega t plus phi. So, if you change it over, and you can write it in a m cos omega t plus phi plus phi. So, there is a phase difference of pi between displacement and the acceleration. There is a phase difference of pi by 2 between velocity and acceleration. There is a phase difference of again pi by 2 between displacement and the velocity. So, when displacement is maximum, velocity is 0, acceleration is maximum in the opposite direction. When displacement is 0, velocity is maximum, acceleration is also 0. Again, when displacement is maximum in the negative direction, velocity becomes 0, acceleration is maximum in the positive direction. So, acceleration and displacement, they are related to each other, they are proportional, but in the negative sense, means if displacement is maximum in the positive direction, acceleration is maximum in the negative direction. When displacement is maximum in the negative direction, acceleration is maximum in the positive direction. So, this shows you the relationship between displacement and acceleration. If you see and compare these two equations, you find pi here. This means the phase difference between displacement and acceleration is 180 degrees, that is pi radians. Again, this slide shows you the relationship between velocity, acceleration and displacement. So, velocity is dxy dt, acceleration is dvy dt, differentiating velocity you get minus omega square a cos omega t plus y. And what is a cos omega t plus y? It is displacement y. So, a is equal to minus omega square y. A is minus omega square y. So, x is given by a cos omega t plus phi, a is given by minus omega square a cos omega t plus phi. So, you can add x instead of a cos omega t plus phi in the equation of acceleration, you get minus omega square y. Now, what do we mean by time period or simply period? I say the time taken for the particle to go like this, move from this position and come back here in the original position. You see, if you consider the wave motion, if the particle is vibrating here in the upward direction, the particle is vibrating here in the downward direction, the particle again starts vibrating in the upward direction at this point. This is called one cycle. So, time required to complete one cycle, this part is what is called one cycle. The time to complete one cycle is what is called time period. We can find out the expression for a time period taking only the magnitude of acceleration. We had seen that acceleration is minus omega square y. Remove the negative sign, you simply get omega square y. So, a is equal to omega square y, or omega square is equal to a divided by y. Take square root on both sides, you get omega equal to under root a divided by y. What is omega? It is 2 pi by t, or t is equal to 2 pi under root y over a. So, time period is simply square root of 1 by acceleration per unit displacement. Frequency. The frequency of the simple harmonic motion is the number of cycles of the motion per second. How many cycles can be taken by a body vibrating in simple harmonic motion in 1 second is what is called frequency. Frequency and time period, as you know, are related with each other as reciprocal of each other. Frequency is reciprocal of time period. Time period is 2 pi under root y over a, then frequency is 1 divided by 2 pi under root y over a, gives you 1 over 2 pi under root of a by y. Now, let us take up the spring mass system. Consider a mass attached to the end of a spring as it is shown here. If the mass is pulled down and released, you pull down the mass, you release it, it will start vibrating and undergoing simple harmonic motion. Time period will depend upon the spring constant of the spring and the mass as given by t equal to 2 pi under root m over k. So, time period of a spring mass system is given by 2 pi under root m over k, where m is the mass and k is called the spring constant. Simple harmonic motion is typified by the motion of a mass on a spring when it is subject to the linear elastic restoring force, which was given by Hooke's law, that is F equal to minus k x. This motion is also sinusoidal in time and demonstrates a single resonant frequency. So, the time taken from this point to this point is what is called time period. It is equal to 1 over f. F is equal to omega over 2 pi. Y is a sin omega t and omega is under root k upon m. T we had done, t is equal to 2 pi under root m upon k. So, omega is equal to under root k upon m. This equation gives you the parameter y, that is displacement. So, the motion equations for SHM provide for calculating any parameter of the motion if the others are known. So, this is how the vibrations take place. This is a mass on a spring, it will trace a sinusoidal pattern as a function of time. Like any other vibrating object in simple harmonic motion does. You can visualize this pattern